Hello, and welcome to a first episode of Applied FuSa, a podcast for FuSa pragmatists. Today, we're providing a general overview of the motivation, goals, and fundamental approaches to functional safety. The aim is to create a common starting point for all listeners, whether you're a complete beginner or a seasoned expert.
Since the dawn of humanity, but especially since the beginning of industrialization, humankind has developed technical systems for nearly all areas of life in order to provide useful functions. These are intended to help perform everyday tasks of all kinds more effectively. Tools, household appliances, vehicles, industrial machines, and even production lines are just a few typical examples of such systems. Systems can be faulty. In other words, the desired function may not be executed as specified, and the outcome may not match expectations. The brakes of a car can fail, the handle of an axe can break, the thermostat of a heater may regulate the temperature incorrectly, the drill bit of a power drill can break, circuit boards may be assembled incorrectly, and traffic light systems can fail. Since no system is completely perfect, there is always a residual probability that a malfunction may occur. The risk of a malfunction is defined as a combination of exposure, severity, and controllability. The more frequently a function is executed, high exposure, the greater the potential damage, high severity, and the lower the controllability of the situation to avoid a hazard, the greater the risk posed by a malfunction. Electrical and electronic programmable systems are referred to as EE systems. Their functions are often divided into three categories: performance, safety, and security. Performance includes the aforementioned functions that are intended to provide comfort or make tasks more efficient. Security functions are primarily aimed at preventing unauthorized access to functions and data. Unauthorized access to functions may occur, for example, when a hacker takes control of a vehicle or a power plant. Unauthorized access to data includes access to banking information, data from a resident registration office, or patient records. Safety functions are intended to reduce the risk of malfunctions. They monitor physical parameters such as voltage and temperature or other functions, and trigger targeted risk-minimizing responses in the event of a fault. Functional safety deals specifically with these safety functions mentioned last. The goal of functional safety is always to minimize the risk that malfunctions pose to the life and health of individuals. The fundamental strategy is to identify all possible causes of safety-relevant faults and to implement appropriate countermeasures. It is easy to imagine that there can be a vast number of potential causes at various levels. The most obvious is a design error, meaning that an EE system processes input signals incorrectly and, as a result, generates faulty output signals. These can propagate further within the architecture into which the system is integrated and ultimately lead to a functional failure that poses a danger to the user. Example: within a sensor, a software error causes the distance from one's own vehicle to the vehicle ahead to be underestimated by an order of magnitude above a certain speed. This can subsequently trigger false braking, which must generally be considered safety relevant. Another example, this time not from the driver assistance area. Within the control unit that controls the windshield wiper motor, the defect of a hardware component causes the windshield wiper to stop wiping without request. A safety-relevant malfunction at the vehicle level is thus triggered by the failure of a hardware component at the ECU level. In addition to design errors, there are manifold error cases in the areas of processes, methods, and tools. These ultimately always generate errors in the design and are therefore to be regarded as root causes for design errors. This does not make them less dangerous, but the relevant point here is that safety-relevant errors ultimately always originate from the product, i.e., occur in the design. The causes, however, are to be found in product development and production. We will now look at a few typical error cases along the product development cycle up to production. It will also become clear that adequate countermeasures can be defined both at the design level and in the areas of processes, methods, and tools, and that safety measures can be defined in all areas of competence when needed. Example 1. The customer delivers a faulty specification. Faulty in the sense that the product risk for safety-relevant errors is too big. Example: the specification requires for a sensor system that the output signal distance to the vehicle ahead be smoothed using a low-pass filter. However, the required time constant has the consequence that during abrupt braking from a certain braking moment, the reaction of the vehicle in which the sensor is installed comes much too late, so that a collision can no longer be prevented. It went unnoticed that a smaller time constant would have been sufficient. If the supplier implements this specification, then the product behaves error-free, insofar as the underlying specification was correctly implemented. The error lies in the specification, not in the product. This is, incidentally, a typical example of the difference between verification and validation. Verification checks whether the product has correctly implemented the specification. Validation checks whether the product fulfills its actual purpose. Or as generally said, verification, check that the product is doing it right. Validation, check that the product is doing the right thing. How could the error have been prevented? What would be suitable safety measures? There can be no blanket answer to this, rather a few hints. Possibly the process on the customer's side is not effective enough to discover and fix every error in specifications before the document is handed over to the supplier. Perhaps the process is also not complete or was not correctly applied. This in turn can have several reasons, such as time pressure, ignorance, unclear process descriptions. On the supplier side, an error could have occurred if, for example, the specification was not a released version, but only a draft. The supplier could have recognized from this that it was not the specification he should implement. In general, errors will always happen, but it is important that the residual risk is reduced to a generally accepted level through suitable measures. Robust processes can be extremely effective measures, provided they are known and understood and are also applied. For safety-relevant error cases, it applies that on the one hand the safety concept provided by the supplier must be implemented, and on the other hand, compliance with a safety standard, such as ISO 26262, should be achieved. Example 2. Technical safety concepts are derived from functional safety concepts, for instance as a result of a fault tree analysis of the system architectural design by the responsible system architect. Lack of experience can lead to the fault tree analysis being carried out incompletely or even incorrectly. Better training, monitoring of results by experienced colleagues, or also reuse of existing solutions can significantly reduce the risk of faulty safety analyses. Example 3. The IFMEDA is carried out with an in-house tool. The tool has a systematic error that leads to increased values for the SPF and LF metrics. Here, adequate tool qualification was missed or insufficiently carried out. In particular, in-house tools must be very carefully tested and qualified. Example 4. Typecasting generates a rounding error in software that results in a safety-relevant error case for certain value ranges. This error could have been avoided if the software had been tested more effectively. Possible methods include thorough code reviews or boundary value considerations. Example 5. Calibration data are not CRC protected because they are stored in a so-called protected area. However, this only protects against unauthorized write access, not against bit flips due to EMC-related disturbances. In this example, it was erroneously assumed that memory protection helps against every type of data corruption. Due to lack of experience, it was not recognized that memory protection is not a suitable measure against bit flips. Example 6. An interprocessor communication breaks down when one of the participating microcontroller works under full load for several hours. This error could happen because there was no suitable test case that checked the stability of the communication even under multi-hour full load. Lack of experience and the absence of standardized test cases can be possible causes. Example 7. Due to defective resistors, the reference voltage for temperature measurement in the engine control unit is too small, which leads to the engine temperature being underestimated. This can lead to overheating of the engine as well as sudden power loss during driving. The defective resistors are so-called single faults because a single fault can already trigger the malfunction. Single faults that can lead to safety-relevant malfunctions are generally only acceptable if the probability is sufficiently low. The described error can have several causes. Possibly it was not noticed already during the concept review that there is a dangerous single fault in the design. If it was noticed, and if a diagnostic function was implemented to detect the fault and react to it, it could happen that the diagnostic function overlooks the fault or detects it too late. For this too, there are again several error causes, such as for instance the concept review of the diagnostic function, as well as the associated test cases. Example 8. Poor solder joints can result in voltage drops, whereby safety-relevant analog signals are falsified. Here there is an error in the production process. Faulty solder joints must be detected and corrected. Another error cause could also be that the process indeed provides for checking the solder joints, but the process was not correctly applied. This in turn could be due to incorrect or ambiguous process descriptions, or to the inexperience of the responsible team. Such error cases are frequently identified by means of PFMEA in order to define measures to detect errors. Those were 8 typical error cases and their causes, 8 of almost countless possibilities from all areas from management through development to testing and production. Errors can happen everywhere because ultimately people are involved and people make mistakes. What have we learned so far? Functional safety aims to reduce the risk of safety-relevant malfunctions of control units. This happens by implementing suitable safety measures for the causes of these malfunctions. The primary cause is always a design error or an integration error, when, for instance, a camera system is installed in the vehicle but is not correctly calibrated. Secondary causes lie in the area of processes, methods, tools, skills. Safety measures should minimize safety-relevant risks. They can address potential error causes at every level. Design errors at system, software, and hardware level, or their causes in the area of processes, methods, tools, and skills. Which safety measures are required must be decided on a case-by-case basis. Typical solutions that are frequently implemented at the design level are temperature and voltage monitoring, protection of memory areas by means of CRC and memory protection, end-to-end protection of communication data. Safety manuals also offer instructions for configuring built-in safety mechanisms for programmable chips. They are developed by the chip manufacturer and can be purchased together with the hardware component. But countermeasures do not always have to be implemented directly into the design to detect errors that occur during execution in the vehicle. Development and production processes consist of a very large number of individual activities whose executions can be faulty for the most diverse reasons, which ultimately can become a safety risk in the design. Safety measures can therefore also aim to avoid these so-called systematic errors. With this, we have reached the end of our introduction to the topic of functional safety. In the next episodes, we will present selected topics that are fundamental for the achievement of functional safety: DIA, impact analysis, the role of the FS manager, safety plan and safety case, functional and technical safety concept, hazard analysis and risk assessment, and much more. So stay tuned, it's worth it.
Applied FuSa, a podcast for functional safety pragmatists. Get your new piece of FuSa every other week.